the old stuff today, just to revisit it a little bit, maybe to extend just for in some more general context. Yeah, and also we have a question. We have to decide what will we do on Friday. So the options are to proceed as usual online, or to meet here either at 4 p.m. 4 something p.m. or at 10 to 5 10 to 5 sorry, 10 to 6 p.m. Yeah. So so what are the preferences?
No preferences.
So okay, and you? Meet here. Yes. At 4 or at 6? At 4.
Well, I prefer to meet live.
Mm-hmm.
At 4, but it's all to. Yes, только если онлайн. Я потому что на Попре в этот момент буду.
То есть вообще у нас некому записывать в четверг, в пятницу.
Да. Да. Это вот такой единственный момент. Либо по-быстрому обучить кого-нибудь еще пользоваться оборудованием, кто гарантированно придет.
So the problem is we will not be able to record the class if it's 4 p.m. Friday in person.
Мы обсуждаем, что делать в пятницу. То есть можно. Да, но вот как бы.
Если вкратце, на этой неделе некоторые несостыковки с расписанием радиоэфирчик, поэтому у нас на семинар на пятницу.
We can record it if it's 4 p.m. but online, or if it's 6 p.m. but in person.
So the options are 4 and 6 online class. Yeah, so who can be in class at 4? Okay, and at 6? Okay, you can, yeah. Mm-hmm. Okay. Yes. So. Yeah. So. But you can only.
Точно подтвердишь, что запись будет.
Да, абсолютно.
Все, вы все равно только онлайн, да?
Я только онлайн, потому что я на Покровке буду.
На Покровке, ага.
С 4.
Понятно. Ну.
Либо с 4, либо с 6, в общем. Если семинар будет, то с 4. Потому что иначе я просто не успеваю физически доехать туда.
Okay. So yeah. So we meet in class, and I'll write you where. So.
То есть еще раз, не класс.
6. At 6 p.m. Yeah. Oh well, 10 to 6.
Аудитория на месте точно.
Okay. So let us just revisit all we have discussed before. So we have we can proceed. yeah, so when you deal with the Galois theory, you can proceed starting from a field to and try to extend it, or you can start with a big field and some group of its automorphisms. So automorphisms, and then you can go downstairs. So you can take the fixed subfield and try to study intermediate subfields of this field extension. So let us take this point of view. So the Galois correspondence actually deals with this situation, but of course it can be formulated in other terms. So the Galois correspondence, I'll just correspondence. So we assume that yes. So we assume that K. So we fix L and assume. So this is a field. Then we assume that K is a subfield. Is a subfield of L. Subfield of L such that there exists a subgroup. There exists a subgroup H of all automorphisms of L, which fixes precisely K in L. Yeah, so actually what I'm trying to...
Isn't correspondence about the existence of such subgroup for any subfield?
No, it's, you see, it's, well, let me give an example. An example of an extension which is not fixed by something, like we can consider so K, let K, small k be a field, and we consider the field of rational functions, and okay, and then we may maybe it's not. You can take sufficiently general polynomial, so p of x. Well, maybe even rational. Yeah, sufficiently general polynomial or rational function. And you can generate by this element a subfield. Yeah, and the claim is that this extension is almost never of this type.
Which type?
Like this. But you see that we have already met extensions. Actually, what I was going to say is that that we consider actually Galois extensions, and you know that not all field extensions are Galois extensions. So you don't really need this particular example because so sufficiently general. So it's not a Galois extension. But you see that, yeah, so the point is that we consider only those fields, subfields that are fixed by some subgroup. But that's not all. So we consider, so assume that L is algebraic over K, is algebraic over K. Yes. And actually, by definition, this means that L over K is a Galois extension. So, but this is just definition. I just remind you the definition of a Galois extension. Okay, and then the claim is that then there is a bijection between there is a bijection between what? Between intermediate subfields.
Excuse me, do we call each algebraic extension as Galois extension? I think that we should.
No. We assume that L is algebraic over K. You see that K is a fixed field of certain subgroup, of certain group of automorphisms of L.
Okay.
So we consider intermediate subfields between L and K, and closed subgroups of closed subgroups of the group of automorphisms. Let me call it G L over K. Yeah, so so by definition, G L over K, well, it is usually denoted by Galois L over K. This is the group of all automorphisms, all field automorphisms of L, identical on K. Okay, all right. So, and the construction is of this bijection is in a sense trivial, and in a sense you can even in principle you do not need to assume that L is algebraic here, algebraic over K. You just you can send a subfield to the group of automorphisms of L identical on F, and vice versa. You send a subgroup here to the fixed subfield of this group. But the question is whether these compositions are identical. Yeah. So what is and to show that they are indeed identical in the case of to show that they are indeed identical, you should assume that this extension is really a Galois extension.
Question. First, is нужно ли это расширение Galois, чтобы оно было квадратическое?
Да.
Да. Okay, so and what we want for the correspondence is just it being Galois extension, right?
Yes. So yes.
And subfields, like all subfields, not just the ones that are specific.
No, all you see that we have a Galois extension L over K, and we consider all intermediate subfields.
All intermediate subfields.
And the claim is that they are all they all come as fixed subfields of certain subgroups of the Galois group. Yeah, so you see that we have to, there is something to check here. Namely, for instance, you see it's written here closed subgroups. Yeah, so, but in particular, this assumes that this Galois group, each Galois group here is closed. Yeah, so we have to check this condition. And maybe I should remind the definition of the topology, yeah, and on this group. So reminder. Well, everything is reminder here. So topology. Topology on. Well, you can say on the whole automorphism group of L. Well, you just say that a base of topology it consists of shifts left or right, doesn't matter. Shifts of certain subgroups of subgroups, namely G of L over K S. So where S runs over finite subsets. Fine. Well, maybe I should.
Gn over K, K of S.
Yeah, maybe I should write here simply F, where F runs over finitely generated over subfields. Subfields. No, finite extensions. Finite. Sorry. We don't have any. Finitely generated. Finitely generated subfields of L. Okay, so you see that this group of automorphisms may be quite huge. Yeah? So, for instance, if we take a field like this, then it contains. Well, just let me give you an example. So, in what is an example which is not related, I should warn you that this example has nothing to do with Galois theory. Yeah, the example is as follows. So if L is the field of rational functions, and we consider, so we may consider the group of automorphisms, for instance, those of them that are identical on small k. Then this is nothing but PGL2K. And then the claim is that this group, if we endow this group with this topology, then this group becomes discrete. So this PGL2K is discrete group. Yeah. Why? Because if we look at automorphisms, we can consider those automorphisms that are identical on a subfield generated by X over K. So it is an open subgroup. So is open but this group is trivial, yeah, because this and this is the same, yeah. So this means that trivial subgroup is open, and therefore all points are open, which means that the group is discrete. This is just to show that there is some contrast between Galois groups and well, sorry? The claim is that the group of automorphisms of the field of rational functions identical on the constants, which is isomorphic to PGL2, is discrete. PGL2, what are automorphisms of this field? These automorphisms are of the following type. They are AX plus B, CX plus D. So for all invertible matrices ABCD, so this is an element of, well, you can consider this matrix as, this is just an invertible matrix, but the group of these fractional linear transformations is the quotient for GL2 by the center, so it's what is called PGL2. Okay, yeah, so right, and actually yes, maybe maybe we should continue to first of all there is this bijection. Well, maybe we should say a couple of words why these groups are closed. So why these groups are closed? So G. Because L and the K of X is the same field. I mean, it's these automorphisms of L identical on this subfield, but they are the same. I mean,
how do you get that PJ2 is discrete?
If you see that this means that the trivial group is open. The trivial group means that it is the element 1 is open, and therefore all its shifts are open as well. So all points are open, and this means that the group is discrete. That any subset is open because any subset is a union of points. Yeah. Now, why these subgroups are closed? So what is why is this? So well, you see that any I don't know. We need some notation for. Maybe we have the field K here. Yeah. So what is this group? What is the group of all automorphisms of L identical on F? You see. No. Now we finished with this example.
Yeah.
We consider the case of general Galois extension L over K. So this.
There is still L is an algebraic extension of K.
Yes, algebraic, and it is a Galois extension. So actually, these are automorphisms of L identical on F. Yeah, and this means that we can present this group as the intersection of what? Of
Galois groups of
Yes, yes. We just take the subfield generated by A over K.
So F contains K, so if the top
Yes,
of
but yes,
okay.
but in principle, if it doesn't contain, well, if you wish to look at subgroups of this, you can put here some prime subfield, yeah, instead of K. So.
Wait, in what sense shifts into place?
Shifts means that actually it doesn't matter. Left, you can write left on right, left or right. So why there is no difference? Because let us write it here. So G F is the same as what? As maybe G. Well, sorry. Well, let's correct this in a second. Maybe it's wrong. Just to make sure. No, it's okay. It's okay. Yeah. You see that. So if you apply this to elements of F, then this acts on F as G. Yeah, it's correct. Yeah, so this is for all G, small g in big G, in G. Yeah, L over K. Yes. So you see that there is no difference between left and right. If right ones, if you consider all subfields. Okay, so yeah, so we present all these Galois groups as intersections of Galois groups over finitely, well, not even finite, not even by generated by a single element. Yeah, so in particular, finite. And what can we say? We say that any so this is an exercise that any open subgroup is closed. So why?
It's open, so its shifts are open, and then we recicle its shifts.
Yeah, and pass to the complement. Yeah, and pass to the complement. Yeah, yeah, that's right. Yeah. So you consider, you see that if you have an open subgroup in G, in some group G, then you say that U is the complement of the union of all shifts of U, which are with the complement of all non-trivial shifts of U, yeah, like this. And all these shifts are open, so the complement is closed. Yeah, so the conclusion is that these groups are
we consider this соединение, оно что конечное, что бесконечное всегда открыто.
объединение открыто.
This union is open, then okay.
Yeah, so this means that so these groups are open, so they are closed. And therefore their intersection is closed as well. Yeah. So this shows that this map is indeed into the set of all closed into the set of closed subgroups.
Closed in this topology.
Yes. Okay. And now, yeah, we have to check that these okay. Now, maybe before certain proofs, let us. So this was the first claim was just the existence of this bijection. So we have constructed. Yeah. So maybe I should just to check that they are mutually inverse. We have. So what does this mean that they are mutually inverse? We have to check that for any f is the fixed field of of the Galois group of L over itself. Yeah. So that's what we have to check, and this is so we know this. So this is we have checked this for finite Galois extensions. And this is for the one composition, and for another one we have to check that for any closed H coincides with the Galois group of L over the fixed subfield. Yeah, so that's what we also have to check. And we also have checked this for the finite extensions. So let's postpone this proof. And what else can we say about this correspondence? We can say that there is bijection. Instead of closed subgroups, we can consider open subgroups. By the way, what is the topology of this group? Maybe we should say more about these Galois groups. So what can you say? So we know that they can be infinite. By the way, can you give an example of an infinite Galois extension and its Galois group?
For example, Q plus square root of minus infinity.
Minus square root?
Root of minus 1.
It's finite. We need infinite.
Infinite.
We can add all piece powers roots of unity to rational numbers.
Okay.
Is Galois group?
This is L, yeah?
Yeah.
And K is, sorry, K is, so you claim that it is a Galois over Q, yeah?
Yeah.
And what is the Galois group?
Periodic integers.
I don't think so. Well, let's see. On the finite level, the Galois group of so you add some p primary root of unity and consider its Galois group. So this the automorphism is determined by the image of each primitive element. Yeah. So, for instance, you can fix some primitive root, and then it can be set. It can be sent also to a primitive root of unity of the same degree, A. So where A is an invertible residue modulo p to the n. Invertible. Yeah.
So it's multiplicative group of the.
Yeah. So you see that these Galois groups. So when you have a union of so our field L is a union of these finite cycloatomic extensions, and its Galois group. Its Galois group is the limit. Do you remember what is the limit? So the limit of the finite Galois groups. And the finite Galois groups, we know them. So these are limit z mod theta then invertibles, and therefore these are invertible periodic integers. Okay, and yeah. So what is clear here that this Galois group is a limit of finite groups. So, and that's always the case. Namely, so maybe I should write this here, that any Galois group is profinite, which means that it is a limit. So it is an inverse limit of finite groups.
Does this just follow from the fact that algebraic extensions are
Yes.
unions of finite?
Yes, that's right. Yes. Just because you present so the reason.
Yeah, but we need the union of normal.
Yes. This because
I'm asking because there is an exercise where you
So-
you ask to prove that every group of automorphism of algebraic extension is profinite. Is it true?
yes, because
But I think that I can construct example where I didn't have any normal subextensions.
okay, but you see that this group may be trivial,
Okay.
so there is no contradiction.
Could you please remind us how does the inverse limit problem works?
Yeah, just a second. Just let us let me repeat after Vladislav and Masha what is why this is, where does this come from, where these finite groups come from. Yeah, so the claim is that any Galois extension is a union of finite Galois extensions. You see, like here we said that our this p-primary cycloatomic extension is actually the union of a finite. I'm sorry, I forgot here n. Okay, and finite Galois extensions like L is the union of Li's, yeah, or LMs, yeah, M's. So where Ln is finite over K and normal, not just normal, Galois extension. And then just to define, what does it mean to, that we have so what is an element of say sigma of the Galois group of L over K? What is this? Actually, this is a compatible system of automorphisms of each ln. So this is a compatible system, of elements sigma n, which are automorphisms of finite Galois extensions. Compatible means that that if we restrict sigma n plus 1 to the subfield Ln, then we get sigma n. Yeah. For all n, and that's exactly that's exactly means that so we may think we may think of sigma as a collection, as a collection sigma 1, sigma 2, and so on, in the product of all these finite Galois groups. And well, strictly speaking, I'm a bit you see that in principle what I'm saying is not completely correct, because our union need not be countable. So so maybe you should just
but we can just
yeah.
order
Yeah.
matrix.
Yes. They are actually ordered by inclusion of subfields. Yes. So it's not completely good. So let us just check. Say that m to n if for any m greater than n, and m greater than n means that m contains Ln. Okay, and here is the same. It is collection of sigma n, where n runs over certain. And the only thing we have to enter here is that this collection should be compatible. And by definition, this means that that this is an element of the direct limit. That is sigma is in the inverse limit. Inverse limit of J lens. Yeah. So okay, and this means that, but know that this product is already compact. So this is compact group of profinite. So compact, profinite in the sense that it is a product of finite groups. Okay, so actually what we deal with is just all Galois groups we deal with are compact ones, but actually there are, as we just saw, there are some other interesting groups like discrete ones and not necessarily discrete. So discrete group is an example of a locally compact group. Yeah? So it is not compact, but it's locally it is. But there are also interesting examples of groups that are not locally compact, but when you deal with some big fields, big in the sense of infinite transcendence degree or something like complex numbers. Yeah, you can try to well, I don't propose this as an exercise, but maybe if you but just a funny fact that that the group of automorphisms of the complex numbers over the algebraic numbers is simple. So if it's maybe it's not that well, I mean it's not hard to prove, but it's not very easy to prove. But if you it is easy to prove that this is topologically simple. Topologically in the sense that it doesn't have non-trivial closed normal subgroups. But actually more is true. I mean for topological proof it's not important that this field is the field of complex numbers, but if you want to prove that this group is simple as just as an abstract group, then it is quite important that the field of complex numbers is big enough in the sense that it's not countable. So it's, well, but topologically you can prove this something similar even if it is countable. Okay, so yeah, now let us come back to this to these questions, and you see that actually what we have to prove here are just statements on the finite level, yeah, because our fields, our groups. So if we, yeah. So for instance, how to prove this? So what is evident? What is not that evident? So first of all, of course, f is included. So f is included into this. Well, for some trivial reasons, yeah. If something acts identically on f, then well, then it fixes the elements here. So the question is, what about the converse inclusion? So we take an element here, okay, and we have to show that this element belongs to f. How do we prove this?
So we have an element A.
Yes, which is fixed by the.
So we already know that F is subfield of this L.
Yeah, because you see, this is trivial. This is trivial because this says that if an element fixes F, then it fixes F. So any element is fixed by an element by the group identical on this F. So this is just tautology. This is just a tautology, but the converse inclusion is not that trivial. It's not trivial at all because in principle this group can be even in general we don't know what is this group. Okay, so but what can we do? We can consider. So we can consider the following field, f prime, which is a finite. Well, maybe not just any field, a finite Galois extension of K containing A. And we know that any automorphism of L identical on yes, so we know that any automorphism identical on wait. Yeah, so maybe we should yeah, and we take intersection. So yeah, we have this field. We have this extension f prime intersected with f. And now we know that that the Galois group of this extension fixes A. Yeah, and on the other hand, yeah, maybe I should erase this. So let's see. So we're
talking about f prime.
Yes, we want to show that A belongs to F. That's our goal. And how do we do this? We know that yeah. So we know that GL over F surjects onto so we know that F is a Galois extension of K, so it is surjects onto F prime. Well, maybe we can write compositum. Yeah. So, for instance, yeah, maybe.
So we want to say that f prime compositum with f over f has the same Galois group as f prime over f prime intersect with f.
Yeah. Just a yeah. So so you propose that to consider the compositum. Yeah.
But maybe we should start with finite Galois extension of f, and then go down.
Yeah, maybe yes. You're right. Yes, maybe it's more convenient. Yes, you're right. So finite Galois extension of f. Yeah. Of f containing well.
Containing
yes, containing A. Okay, and then yes, you're right. So then we have a surjection of the Galois group of L over F onto the Galois group of F prime over F. So this is surjective. Yes, and also we know that this group F prime, this group fixes precisely F. Yeah? And on the other hand, the action of this group restricted to F prime coincides the action, the G.
Why did we decide that F prime is an extension of F?
We want this. We just construct.
Okay, so we construct such F prime that.
Yeah, we take any Galois extension of F containing
For
A.
example, by joining A to.
We adjoin A and then we take its normal closure. Normal closure in the sense that we adjoin not only A but the whole Galois orbit of A. Yeah. So here it is written a finite Galois extension, but we can find instead of this we can say that F prime is just F with adjoint Galois orbit. Galois orbit of A. So, but it doesn't matter. You can take any other Galois extension.
Orbit is just orbit of the
Galois group of the Galois group, the whole over F. Over F. Yes, because we want a Galois extension of F. So over F, yeah. So over. Maybe I should write this more explicitly. L over F orbit. Okay, yeah. So and that's so this the action.
But we didn't know at the moment that this orbit is not trivial. Is it okay?
It's okay. It is, yeah.
What we're doing is we're proving it's not real.
Yeah, but maybe it should be over K, not over F.
Is there even a difference?
Yeah, okay, maybe but what do we want? We want yeah, let's see what we really want. What do we really want? So we want the following thing. We want a surjection like this, yeah? If we do have such a surjection, then of course, then the action of this Galois group on F prime factors through this quotient, yeah? And then the fixed field of this group on F prime is the same as the fixed field of the Galois group of F prime over F. And this is F.
But what if all normal extension of F, contains... okay.
You see that for finite extensions, we do have
But the problem is we don't know if the orbit is finite.
sorry, the orbit.
No.
We do. We do because for many reasons. but one of them is that what is A? A is what is A? A is in a finite extension of f, so it is a root of certain irreducible polynomial over f.
Why is it a finite why do we know it's
Because any element of L is you see that any algebraic extension is a union of finite extensions. And so A is a root of certain polynomial over f, and any automorphism over f sends a root to a root. So there are only finitely many of them. So the orbit is finite. By the way, this this in particular, well, you know that the stabilizers are always of finite index for this reason. The stabilizers of A, they are open, first of all. They are open and they are of finite index. They are open by the definition of this topology. And because this is so these are all this is a variation on this profiniteness property of the Galois group. Profinite means that essentially this means that any open subgroup is of finite index. Because yes, because you can think of this group as the limit of quotients by open normal subgroup. So yes, so maybe yes, so you can something like this. Yeah. So what was our
Actually, we need only one such extension because
yes.
Okay.
But just so one more time. What do we need? We need. So assuming that we have such at least one extension like this, where this restriction is surjective, then we are done. Yeah. So the question is, why do we have this?
Because alpha is algebraic inseparable, and so.
And what is alpha?
Sorry.
A
A.
algebraic inseparable, so we just can build by hands this extension of f.
How do we construct this rejection exactly?
Well, this is just restriction. Just restriction. You have an automorphism of L, and you restrict it to f prime. But
so this rejection is just the restriction to f prime.
yes. Yeah. The question is, so the question is why do all automorphisms of f prime extend to L?
By its own lemma, somehow.
Well, we have this theorem that
Yes. Yes.
it's extendable.
Okay. So this shows equality here.
Why
why did the suggestion happen?
Well, the suggestion happened because we take some phi from the left group, and then we.
From the right, and then extend.
All right, yeah.
Yeah. So phi is an automorphism of f prime, and we. The claim is that we can extend it to
any algebraic
well, it's not quite true.
no?
No. No, to any normal. To any normal extension. Because you see that. Because it may happen. For instance, take q f prime equals to f equals to q, and sorry, no, it's not interesting. Sorry. Oh, maybe you're right. Maybe you're right. I'm not sure.
We say that L over F prime is normal, or what's the number?
Yeah, f prime over, yes, f prime over f should be normal, of course. Because otherwise,
No, I mean, if we say that we can extend phi to another version of L by this theorem, then we have to say that L over F prime is normal, isn't it?
L over f prime, yes, L is normal over every intermediate subfield.
Why?
Because
we have some different definitions of normality. One of them is that if polynomial have one root at L, I mean polynomial with coefficients in F, then it has any root.
Then all of its roots.
It's not huge. Okay, we can say that that extension is normal if the image to some any bigger extension is not dependent on inclusion. So if it's not dependent over some small field, it's obviously not dependent over some bigger field. No?
yeah, so what you're saying is that, yeah, so for instance over k, yes, so for instance you have an embedding into, well, say omega, yeah, so and if, yeah, so the claim is that it's this embedding, the image of this embedding with fixed embedding of k is independent of this inclusion, yeah? And then if we fix an inclusion of a bigger subfield, then of course the image of this horizontal inclusion will be again independent of the particular choice of this embedding.
Could you please write down the independencies?
Yeah, so so this is fixed. This is fixed. Fixed. This is also fixed. And we consider those embeddings that such that diagram commutes. Yeah. So so phi. Well, psi, and so psi of L is independent then of psi. So this is definition of normality. Of normality of what? Of normality of L over K. Yeah. So L of K is normal. If yeah, and now if L over K is normal, and instead of K we consider inclusion of an intermediate field, then of course the image is also independent of this embedding. Yeah. So then L over F is normal. So where F is an intermediate subfield for any K, F, L. Okay, so yeah, so it's not so this from the upper side it's not a problem. The problem is that here we have to have a normal extension F prime over F, yeah, and this is yeah. Okay, and then yes, and then you're right that yeah. So actually, we need F prime to be normal just to define this restriction, because otherwise the automorphisms of L need not to preserve F prime. Yeah, so they will not induce automorphisms of F prime. So that's the condition. But then, of course, you can extend it to. Yeah. So we have this. Yeah, so actually here as omega we take simply L. You see that so here omega is equal to L. And we say that so we have inclusion of F prime into so omega is F prime. Yeah, and K is F prime. Yeah. You see that here we take F prime. It is embedded into L identically, and on the other hand, it is embedded into again L via this phi. First we apply. Yeah, maybe I should write this. So we take L F prime. F prime is embedded into L. Then it is embedded into L using phi. And the claim is that there is an embedding of L into L, making diagram commutative. Yeah. Okay. Yeah. So, but this is just only one half of the correspondence, and another one is for this group, and for this group. So what can you say? Of course, here we have to. So what is evident here? Of course, this group is contained. This group is because it acts identically on what is fixed by this group. Okay, so we have to and using some just general words, we cannot prove the converse inclusion because this group may be in principle there are other groups which are not closed. Yeah, some dense subgroups. For instance, here, well, in the example with cyclotomic extension, we could take not the whole periodic integer, invertible periodic integers, but only, for instance, p invertible p integers, so rational numbers, yeah, and the result will be the same as for its closure, yes, for the corresponding periodic numbers. But yeah, so here we have to proceed the following way. Actually, the idea is the same. So, how do we prove this? We just look at again at finite extensions. How could we do this? Yeah, so we present L as the union of Galois extensions. So there's a finite Galois.
So the inclusion of H in this group is
Thi-
trivial.
yes, this is trivial.
Okay, it's trivial.
Yeah, then we have to prove the converse inclusion on the assumption that H is closed. Yeah. So what do we actually want to prove? Actually, we just consider all finite, well, at least some. We present our field as a union of finite Galois extensions, and just a second, I have to, yeah, it's okay. Finite Galois extensions, and then restrict our H, so we can consider restriction of the big Galois group to these subfields, so we can map. This is denoted by H and the image. So this is the image in the Galois group of Ln over K. And the claim is that it's sufficient to suffices to show that Hn coincides with.
Maybe we should take only the fields Ln which contain invariance of H.
No, we can't, because invariance of H can be infinite over. For instance, if you take 1.
Yeah, but what is the map which sends H to Hn?
No, Hn, this is notation. This is just the image. So you see that we have a map, we have a restriction map. We have this one.
Okay.
And the Hn is just the image of this map.
But
You just restrict the action of the group on the subfield Ln, and the image denoted by Hn. Yeah. So the claim is that it's sufficient to prove that Hn coincides with the Galois group of Ln over the fixed subfield of Ln. Yeah, but this is just usual Galois correspondence for finite extensions. Yeah, so you see that. So why this is sufficient? Because that's our topology. That's our topology in the sense that H is so maybe. So in general, we don't have this. Inclusion, but what we do have, we have the following equality, that this Galois group coincides with the inverse limit of hns. Okay. Is that okay? Or
And so maybe the problem is I still don't understand what is an inverse limit.
this is it's you should look here.
Well,
It
I
is-
asked you this discussion before, but it's
Yes, and I have answered your question. This is the inverse limit. These are compatible.
This sigma m. Of
These
m
are collection.
How to read this sigma of something is from this production.
Product, yeah. So you just for each n you have certain sigma n, which is an element here. This is just a collection, big, huge collection, and the condition. So this is called a product. This is called a product. But
So the question is how do so what is this element sigma n?
no, it's not. This means just. This means that you have certain. Certain set of indices, and this means that n runs over this set of indices.
So we fix sigma n and
You fix this collection. Yeah.
So we just take this something like a vector from
Yes,
okay.
but the coordinates of this vector should be compatible.
So I just didn't understand how to read this.
Mhm.
And then the sigma that is this vector is an inverse limit or
It is an element. It is an element
yes,
of
this is some element. And
yes of the inverse limit. So maybe the most
maybe
some examples.
yeah,
Yeah,
maybe-
some.
well I still don't understand.
So
Okay, so sigma is a collection, and then we say that sigma. So this inverse limit is a collection of all such collections.
Yes, in a sense, yeah. Compatible means that you see that maybe you should start with an inverse system. Inverse system means that you have a collection of, say, groups, for instance, yeah, like this, and certain maps between them, certain homomorphisms between them. And compatibility is understood in the sense of these maps between them. So, for instance, if you have well, how it's called, discrete inverse system, you just have some groups or sets and nothing between them. Then what you get is called the direct product. Yeah, and if there is something between, well, maybe I think we have already mentioned this example. If as a set of groups you consider residues modular powers of a prime, like z mod p square, and so on.
Maybe the example with formal series is simpler one.
Yeah, or maybe with formal series, yeah, you can take say a ring and then polynomials modular t square, then polynomials modular. You mean that everyone knows what is a formal series? Yeah. Okay. Yes, you're right. Yes, you can take polynomials modular t cube and so on, and then the limit, the direct, inverse limit.
Polynomials modulo t square and then modulo t cube.
T cube and so on. Yeah, and so on. And then you can identify. So you consider polynomials modular powers of the variable, And actually, you can identify the inverse limit with the formal series. And so formal power series, and is better, yeah, because so how do you think of compatible systems of truncated polynomials? So you see that this system consists of truncated polynomials, yeah? Polynomials modulo t square, and so on. But actually, if they are compatible, then to any compatible collection, you can associate just a formal series. So its constant term will be what you see at the very beginning, and then you modulo t square, you will see its first two terms, and modulo t to the n, you will.
То есть это как поэтические числа. Сейчас. Все. Да, все понятно.
Yeah, and moreover, in we had already example where the Galois group was presented as invertible integers, periodic integers. Yeah.
What we did with the proof, we said that there are the HNs, and we said that what was the inverse limit, the Galois group of L over LH?
Yeah. So so the claim is that in general, if you start with any subgroup H, then the Galois group of the of our big L over the fixed subfield is not H. It's not H in general, but it is its closure. It is its closure, and its closure is presented as the inverse limit of HNs. So this is the closure. So this is the closure of
Why is
H.
that? Why isn't the inverse limit?
Because
We can say that our group is Hausdorff, and we can just take a sequence of elements that converge to each element from this inverse.
yeah, you see that what is a Galois group? A Galois group is the inverse limit of Galois groups of finite Galois extensions, sub-extensions.
And we're saying that the HN is
HN is exactly the Galois group of a finite Galois extension.
okay. Why is that?
This is just usual finite Galois correspondence. You see that, so maybe, so what have we discussed before? Yeah, so we have Galois correspondence between, in the case of finite extensions, finite Galois extensions, we have just bijection between all subgroups of the Galois group and all intermediate extensions. And here, in general, we only have correspondence between closed subgroups and all intermediate extensions. Maybe I should also add that there is a correspondence between, well, it is.
Why is if H is closed, then it is the inverse limit of HNs?
You see that, so if Hn is closed, then
If H is closed.
yes, if H is closed, then it is already profinite. So it is it coincides with the inverse limit, because wait.
You can use simple topological argument. It's easy to see that GL over LH is Hausdorff. So if we have morphism from H to Hn, so we can just take a sequence of elements which converge to any element it's in this group. But we have taken each element in H.
Maybe we should first of all we do have a map from H to the inverse limit, yeah, because Hn, yeah, because we have a surjection onto Hn on each. For each n, we have a surjection from H to Hn, and
so this map is surjection.
this one,
Or
no, it is not in general. You see, it's surjective onto Hn, but not on the limit. Because the point is that this map is, first of all, it is injective. And because, as Vladislav said, it is Hausdorff. So the what is the kernel? The kernel is what is the kernel? The kernel is the subgroup acting trivially on all ln's. Yeah, and this means that this kernel acts trivially on the union of all ln's, and the union of all ln's is the whole L. Okay, so it is injective.
Why is it injective? Because its kernel acts trivially
Since,
on all ln's.
its kernel acts trivially on all ln's. So acts trivially on the union. On the union, which is L, and the only element acting trivially on the L is the identity. Okay, and yes, and actually this condition that H surjects onto Hn exactly means that H is dense in the direct limit, in the inverse limit, I'm sorry. Because how do you define, that's the question, how do you define topology on the inverse limit or on the product? Yeah, the topology, you define it as shifts of the kernel of this map. So you see that this means that so any element in the inverse limit can be approximated by a certain element here. So you take an element here, and you find an element in H, which goes to this element. This precisely means that it's like you should think of this as inclusion of Z into ZP, into the periodic integers. Yeah, so this is precisely the same. Or if you wish, polynomials into a formal series.
And you will say that if H is closed and dense,
Then yes, if it is closed and dense, then it is the same, the whole limit. Yeah. Okay. Yeah. Well, just briefly, I have to run. I think. Just I stated as an exercise. So open subgroups. Open subgroups.
Then, how did we get that H coincides with G with this group?
H coincides with this group
Yeah.
if H is closed.
Yeah.
It is dense
Mm-hmm.
and closed.
Mm-hmm.
So its closure coincides with this group, and it is already closed. Yeah. So open subgroups they correspond to subfields F. Well, they are such that they are finite over K. So we already have correspondence for all closed and arbitrary intermediate subfields, but for those that are finite over lower field, we say that they are open.
And how exactly do we create the bijection?
We should just.
This is just restriction. So this is the same bijection as before, but the claim is that because any open is closed, so we get this. Well, anyway, we can go this direction.
So we need to check that open subgroups corresponds to finite fields.
Yes. The opposite is evident. Yeah. Okay. So see you on Friday. Okay.